Right. Good morning. Any questions, comments? So today I want to talk about type 2 superconductors and something called Abrikosov vortex lattice. So let's clean up what we did so far and let's try to review. So the starting point is we write some free energy compared to normal metal, and we wrote this free energy in the form like let me write 1 over 2m P minus Q over C A acting on order parameter psi squared plus A squared plus 1/2 B psi to the fourth. So this is what we call the matter free energy, and on the top we edit this Maxwell term 1 over 8 pi, or like field energy curl of A squared. So this integral is taking the entire thing, and from the minimization we found a set of equations. The first one was what is sometimes called Ginzburg-Landau equation. So this is 1 over 2m P minus Q over C A square acting on psi plus A psi plus B psi squared. B is equal to psi is equal to 0. So this is the first equation, which we called nonlinear Schrödinger equation. We found a current, and the current was minus I Q H bar over 2m. Like this is usual quantum mechanical current. You are probably familiar. Psi minus psi curl nabla psi star. So this is the usual current, and we also have so-called diamagnetic term. So this is Q squared over MC psi squared A. And lastly, so this is 1, this is 2, and last one was we found this Maxwell equation. Good. And pretty much everything about superconductors we try to explain using this set of equations. Let's also review what we did. The simplest thing was uniform case. Uniform case. So this means psi is a constant and all the gradients drop out. In that case, Js is going to be equal to minus Q squared over MC, some psi 0 squared, and A. And if we take the curl of both sides, let's do that real quick. This is curl Js. This is curl A. And for curl Js, I also can use this equation. So this is going to be this side C over 4 pi curl of B, and this side is of course curl of A is magnetic field, and we expanded this as del squared B minus del dot B and this thing is 0. And from here we found del square B is proportional to B. Okay, this is also vector, and we have this for each component. Therefore, we had del squared B is equal to something like 1 over lambda squared B. And if you collect all of these coefficients, 1 over lambda squared was found. Actually, let me write lambda. Lambda is equal to mc squared over 4 pi q squared psi 0 squared, and this is root. Also q here we said is equal to minus 2e, 2 electron charge, and m is equal to 2m electron, but this is not as important as this one because this can be absorbed in the definitions. So this is what we called London penetration depth. So this is how much the magnetic field can enter inside the superconductor, and because of this equation we said it's going to be exponentially decaying and it will not be able to enter the superconductor. Now, how do we find psi 0? We find the psi 0 from bulk superconducting free energy, and it is something like that. Fs minus F normal is equal to sum A psi 0 squared plus 1/2 B psi 0 to the 4th. And we take the derivative like 2A psi 0 plus 2B psi 0 cube and set it to 0. Then psi 0 was found to be minus A over B. And from here we said A should be something like A dot T minus Tc, so that when T is less than Tc, A is negative, negative is positive, and we have like a positive norm order parameter as we should have. Whereas when T bigger than Tc, this is 0, right? That's what we said. Therefore, this London penetration depth written in terms of this, you just substitute this psi to here, and what we find is the function of temperature. This is mc squared B divided by 4 pi q squared A dot T minus Tc, and it diverges as a function of T minus Tc to the power minus a half. And a second scale was obtained from like neglecting the magnet. So far we were trying to understand how magnetic field enters the superconductor. We can also say like there's no magnetic field, and let's look at this equation for the order parameter. And from here what we found was something like that. Let's set A is equal to 0, then let me for simplicity use 1d h bar squared over 2m d squared dx squared psi plus a psi plus b psi cube. We also solved this equation, and from here we found a second length scale, and we call this like superconducting coherence length, and it was given by h bar squared over 2m a, and it was h bar squared over 2m did I reduce a dot Tc minus T, and this one also diverges like this is T Tc minus T to minus a half as you approach critical temperature. Therefore the picture is something like that. Let's say this line is separating a superconductor from the vacuum. So this side is vacuum. So this is superconductor, and let's say this is X, and magnetic field inside vacuum is some external magnetic field you apply, but what happens is like superconductor just swallows, like expels this magnetic field. So this is B, whereas inside the superconductor we need order parameter, and order parameter from the solution of this equation we know is going to be vanishing at the boundary because there is no material, there is no superconductivity, and it's going to be something like that. So there are two length scales. The scale of superconductor is psi of t, and scale of magnetic field is lambda of t. Therefore, there is a question of which scale is dominant and which scale is not, right? That also enables us to introduce so-called Ginzburg-Landau parameter. So this is like a Greek letter kappa is equal to lambda over t over psi of t. And if you we have lambda here, we have psi here, and the temperatures are going to cancel because they have the same temperature dependence. At the end, this kappa becomes mc over h bar q. Let me put it like this: b over 2 pi. Good. Now I want to consider type 2 superconductors. And the picture was something like this. So we have this minus m, and we have this external applied field, and there were two critical fields. We called it HC1, and actually this one is like generally much larger. It can be all the way to almost comparable to Tesla. So this is HC2, and what happens is like until you reach HC1 you have perfect Meissner effect. You completely expel the magnetic field, something like that. But after that, magnetic field expulsion is a little bit more inefficient, and magnetic field leaks inside the superconductor, and at HC2 there's like so much magnetic field you destroy the superconductivity. So that's the picture. So this is what we called Meissner phase. So this is sometimes called mixed, or sometimes also called Abrikosov phase. And this side is normal. So you can see here, like superconductivity is almost killed. Therefore, we can like expand. Okay, let me first write the free energy, or like a Ginzburg-Landau equation, which is 1 over 2m p minus q over c a acting on psi plus a psi plus b psi squared. Psi is equal to 0. However, like here, like I said, superconductivity is almost destroyed. That means the order parameter should be very small. It should be vanishingly small. So then there's a good reason for us to neglect this term. And then we can think about adding it later. So let's drop this term, which is done by Abrikosov, and we need to solve this equation. And to solve this equation, right, I can also assume again, in the vicinity of this region, I can assume that the magnetic field is now entering the superconductor uniformly, and I can think about like a uniform applied external magnetic field. And applied magnetic field is equal to physical field inside the superconductor. So uniform field, let's take B is equal to some minus B times Z. And the vector, we need to choose a vector potential, right? There's like a gauge degree of freedom, and here I want to propose to use this vector potential. This is 0, Bx 0. So this is Landau gauge. A lot of things for Landau's name, but that's how it is. And you can check, right? This is, let's check del cross A. So this is del x, del y, del z, 0. And the only component is the z component. So this is plus minus plus. This is minus b times z. Now I can like, okay, there is also square here. Now I can try to unpack this equation and try to look if we can solve it. Plus, and I have, sorry, this is plus, and this is x and y. I think this is plus, right? Does that make sense now? Yeah. Okay. Yeah. So now I'm going to unpack this, right? There is like x component. The x component is minus. So there's p is equal to minus I h bar gradient, and x component is going to give us h bar squared over 2m del squared del x squared plus y component. Y component, you can see there's like a y component here. It's going to be 1 over 2m minus I h bar del y minus q over c bx squared. And lastly, the z component. Z component, there is nothing, so this is h bar squared over 2m del squared del z squared. And this entire thing is acting on psi. So this is acting on psi, and we also have this term, this a, and I'm going to write it like minus a psi, and we know inside superconductor minus a is positive, so there is like a positive quantity inside superconductor. Now I ask you, so I look at this entire operator, so there is derivative of x, derivative of z, but there is only one x-dependent quantity, right? The x-dependent quantity is here, and there is no other y or z-dependent quantities here. So maybe I ask you, is there like translational invariance, for example, along x? Do I have like a translational invariance along x? No, right? Why? Because I have some x here, right? They don't commute, so p and x commute, then there is no translational invariance. Is there translational invariance along y? Yes, right? Because there is no y, there is only derivative of y, so translational invariance along y, and similarly z, right? There is also no z. Then I'm going to substitute for this psi something like this: e to the I ky times y plus I kz times z, some other function phi. And this phi will only depend on x. Is that okay? Then this is going to be this term plus 1 over 2m. So here every time I take the derivative, I'm going to have minus I h bar times I ky minus q over c bx squared, and here I'm going to have plus h bar squared kz squared over 2m. Right? This entire thing is sitting on psi and giving us minus a psi. Good. Now let me clean up. Minus I times I is plus, and I have h bar k here. And what I want to do is I want to take this qb over c outside. So this is going to be q squared b squared over c squared. And okay, let me do this. So I take this out, and I need to divide this thing. Like, let me open up some space. So I need to divide this by qb over c. Now I am trying to see what this term is going to do. So I can do the following. I can put m squared here, erase this, and this is, okay, 1/2, and I can multiply with m. And now if I introduce so-called cyclotron frequency, omega is equal to qb over mc. So this thing is omega squared, right? I can erase this, and I can put 1/2 m omega squared here. And now I can see h bar over qb over c is equal to, I can do the following. I can put m and m, and now it is going to be h bar over m omega. And does anybody recognize this quantity? More elementary, like from undergraduate. This is harmonic oscillator length, right? So this is L squared. So I have this, then I can write this, erase this, and I can write this like ky L squared. Actually, let's also define one more thing. I want to call this x naught, and I have to remember it depends on ky, is ky L squared. But what is important for us is it doesn't depend on x, right? Then it is like x naught, but x naught minus x squared is equal to x minus x naught squared. I have this. Good. And lastly, I want to take this to this side, right? This h bar squared over k to this side, and I want to define some epsilon is equal to, if you want, absolute value of a minus h bar squared kz squared over 2m. I can write it like epsilon, and I can erase this. Okay, now we are done. And I think everybody should be able to recognize what is this equation. Huh? Harmonic oscillator, but shifted, right? Shifted harmonic oscillator, and the important thing is this center of harmonic oscillator is ky dependent. Then once we see that, we are happy because we don't have to solve this equation. Energies are quantized, and they are going to be h bar omega n plus a half, and they are going to be n is equal to 0, 1, 2, dot, 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 and the ground state n is equal to 0 is ground state, and the corresponding wave function psi of x is proportional to e to the minus a half L squared x minus x naught squared. And now we observe this, and we say that look, so minimum energy is h bar omega over a half, and this is given to be absolute value of A. Where did we define it? Here. We define it here. Minus h bar squared kz squared over 2m. And this equation, right, this is like a positive quantity. This side should also be positive. And to get the minimum energy, I can put, like, let's put kz is equal to 0 and get rid of this term. Okay. Now I want to write what this thing is. So h bar omega is qb over mc. This is 1/2 is equal to A. Let me write it like this.
But we said A was negative.
Yes, right. Like A, we are inside superconductor. So this A is A dot T minus Tc, and it is negative inside the superconductor. Now we carry it on the other side. This is like minus A. This is positive inside superconductor, right?
Okay.
And if you want, I can put absolute value, but it's something like that. But what we want to find is like what does this equation give us for a magnetic field, right? This is the maximum possible magnetic field. Let me define it like B max, and it is defined by. Actually, let me define it a little bit more carefully. B max from this equation is going to be defined as RHC2, the second critical field, and it is going to be 2mc over h bar q times A. 2mc h bar q over M. But I want to compare this. So this is like previously we found HC1 from thermodynamic equilibrium. Like okay, let me also remind you, because I have a little bit time. Previously, so this Fs minus Fn is equal to A psi squared plus 1/2 B psi to the 4th. We minimized and we found this psi squared is equal to minus A over B, and then we substitute this back here, and we found Fs minus Fn was equal to minus 1/2 A squared over B. I just substitute this psi and there's cancellations, and we said this free energy difference should be equal to amount of work you do to expel flux, right? Expel magnetic field. And from here we set this to minus HC1 squared over 8 pi. From here we found HC1 is equal to, okay, this is 4 pi A squared over B, and there's like a root. Good. Now I want to compare this HC1 and HC2, right? Let's look at HC2 over HC1. HC2 over HC1, and this is going to be, let me just copy. So this thing divided by actually root, so this entire thing, and let me write it like this. So this is root, I'll take 2 outside, this is root pi, this is A, and this is going to be root B, and I'll cancel this A with this A. I'll cancel these 2 with these two, and I have this is equal to mc over h bar q. mc over h bar q. I have root b and pi. Okay, yes, this is b over pi, and I want to multiply this with root 2 and write this 2 pi, and I look at this equation and I go back. Where did I find it? Okay, here. Let's compare it with this, which we called Ginzburg-Landau parameter, which is lambda divided by xi. So I have mc over h bar q, mc over h bar q, b over, okay, this is exactly equal to root 2 times kappa. Now I can erase this, right? But now I look at the phase diagram. For all of this to make sense, right, hc1 should be less than hc2. I mean, if this calculation gives like some hc1 above hc2, that's nonsense. And that should be the threshold. Therefore, I require this root 2 kappa to be bigger than 1. Then type 2 superconductors are possible if this root 2 kappa is smaller than or equal to 1. There is no type 2, right? That's nonsense. Then I'm going to call it type 1. Then the threshold is, okay, let me write this like 1 over root 2, and this is 1 over root 2, and erase this. There's another nice way, okay, of seeing how this threshold determines this HC2. Let's consider this HC2. HC2 is equal to 2mc divided by h bar q times a. I just copied this thing exactly. And what I want to do is I want to use this coherence length we found. Coherence length was h bar squared over 2m a. And so I can do the following. Let me just copy and let you see what I'm doing. So I want to do this h bar squared, and I want to put it h bar here. And I want to take this 2m here and erase this one. And I want to take this a from here and put it here. And you can see this is coherence length squared. So this is, and there is h bar c over q. So h bar c over q, and I want to write it like 1 over 2 pi h bar c. So what was this quantity? Does anybody remember? hc over q. Exactly, yes. This is the flux quantum. So this is flux quantum. Actually, let me write a little less obnoxious color. So this is flux quantum divided by, there's like 2 pi, and h bar squared over 2ma is xi squared. Good. And the nice interpretation I like about this is there's like one flux quantum. So this is one flux quantum, and this is area. If we interpret xi squared to be the size of the Cooper pair, this is the area of one Cooper pair. We don't know Cooper pair yet. We are going to talk about this, but we have a sense that superconductivity takes place because of electrons pairing to form a boson. Therefore, whenever you try to put more than one flux quantum per Cooper pair, you destroy the superconductivity. That's the interpretation for HC2. Good. So I want to do one last calculation and we can take a break. So let's think about the wave functions. So Abrikosov considered psi in n is equal to 0 only. Right? I am saying that in the low energy limit, I only populate the lowest available state, and this is called generally lowest lambda level. And the wave function there is like, so if n is equal to 0, we have like a wave function which depends on x, or there is like some normalization constant which we don't care, but this is just Gaussian. This is 1 over 2L squared x minus x naught squared, right? So let's think about this a little bit. So this, let me write what L square is. L square is h bar over m omega, or L is equal to root h bar over m omega. And we found B max is equal to 2mc divided by h bar q times A. Now I want to put this Bmax inside this L and see what this gives me. So this, let me write it L square, not write root h bar over m, and omega was qb over mc, and this is, okay, cancel this, h bar c over qb. Now I'm going to write this b max here, so this is h bar c over q 2mc over h bar q times A, and cancel c's, cancel this, and you can see this is going to give us h bar squared over 2ma, and this is exactly our coherence length squared, right? Then harmonic oscillator length becomes the superconducting coherence length in that region. Then we can write this as psi of x is proportional to e to the minus 1 over 2 psi squared x minus x naught squared. Now I have to think about x naught a little bit. So x naught was equal to ky times L squared. And I need to choose something for ky, and typically we choose periodic boundary conditions, right? We are saying that we have e to the I ky times y type of solutions, and we require these solutions ky times y plus some finite size in y direction, and this gives us ky is equal to 2 pi over Ly times some let me call this ny. This is not the harmonic oscillator, this is like a Neve quantum number, and this x naught becomes ky L squared 2 pi over Ly ny, and L squared I'm going to write h bar over mqb over mc, like a lot of cancellations. And I want to write this in terms of flux. let me multiply with flux phi naught and divide by flux, and dividing is hc over q. Then so this q cancels this guy, so this h bar, and okay, this, let me do this h bar, 2 pi cancels this one, this c cancels this one, and at the end there's nothing, basically n y. Let me just write n because it's already cluttered and we have lowest Landau level, there's no other n anyways, so this n phi naught divided by b ly. Good. So the center of, okay, each ky has a different center in the Gaussian. Okay, and since all of them are degenerate, right, they are all in the lowest Landau level, and any given order parameter should be linear combination of all of these degenerate states. And using this, Abrikosov wrote like this psi. The only important is x and y components. Let me write these and neglect all the others. So this one is ny is equal to minus infinity to plus infinity. So this is ny. So there is like some expansion coefficient. So there is this e to the I 2 pi over ly times ny times y, and we have e to the minus 1 over 2 psi squared x minus n and y phi naught over b ly squared squared. Good. And he considered this to be, if you want, variational parameters to be found from the energy minimization. You can see this equation is already periodic in y direction, right? Because that's how we built in these factors. As soon as you shift y, you have periodicity, but no periodicity in x direction. But we can impose this periodicity. Let me show you how to do this, and then I'll take a break after that. Let's take this wave function and shift it and see what we need to have a periodicity in x direction. So what I will do is I want to shift this by another Lx, and I want to look at it and I want to see what I need to have periodicity. What I need to do is I need to, wherever I see x, I need to put x minus Ly.
Alex.
Sorry, Lx, yes, Lx, absolutely. And now I will look at this, like, and I say myself, if I can combine this vector with this vector, and I can, okay, this is also ny, by the way, and if I can find a way to relabel the summations, I have a chance to have periodicity in x direction. So let me do this. So if I have, so this thing, right, what do I have here? I have ny times phi naught over b ly squared. If this ly is equal to phi naught over b ly squared times another integer, let me call this mu, and mu is integer, I can combine mu and ny, and I can relabel this summation and see if I have periodicity. Then let's do that. This is going to be so let's write one more time. So what I will do is I'll erase this And I'm going to write this minus ny plus nu. Good. But now this I want to define a new summation variable. Ny tilde is equal to ny plus nu, or ny is equal to ny tilde minus nu. Wherever I see ny, I need to write ny tilde minus nu. So this is the first place I see ny tilde minus nu, and here this is ny tilde minus nu. Good. And I need to also change the summation to ny tilde. Now here you can see this new form. I'm going to take it outside. So this is e to the I 2 pi over Ly. There's like a minus nu times y, and the rest is I can just write times the same thing. Actually, let me try to combine a little nicely. Now there's only, okay, this one is gone, and here in this equation I have only ny tilde, so I can forget about tilde because it's just a label anyways. And this is ny, and this is ny. And last thing is, if I require c ny minus nu is equal to c and y, this equation is exactly like psi x comma y, and this equation is e to the minus I 2 pi over Ly nu y. Now I have some people from 410 last year. Does anybody remember what this factor was? I think it's a little bit technical, so I don't anticipate you to remember, but if you want to see this, so this is called generalized Bloch condition. Typically in the Bloch, right, the whole time what we were trying to do is we shift by Ly and try to see how it is related to this, right? And in the conventional Bloch vector, we have, I don't know, x. If you shift by a, you have e to the I k times I times psi k of x. But in 2D, under magnetic field, translation operators in x and y direction, they do not commute. And you need to redefine the Bloch condition in the presence of magnetic field. And then if you redefine the Bloch condition, this is exactly what you find this factor. And if you want to know more about this, maybe I can give you the reference. You can read Gerwin and Young, Modern Condensed Matter Physics. It's in section 12.9. Good. But the upshot is, this is enough for us to have periodicity in x direction too. So before I finish, let me comment about this condition. So if you look at the paper by Abrikosov, he says there is no reason to consider anything other than nu is equal to 1, right? He says he wants to take nu is equal to 1. And then if you, of course, in his times there were no computers. He could only take 1 or 2 expansion coefficients because he was doing all of these things, I think, with his hand. And then if you take nu is equal to 1, you find square lattice. Square lattice. And we are talking about vortex lattice, right? So the vortices enter the superconductor, and they form the magnetic field enter the superconductor, and they form vortices, and these vortices arrange in a crystal lattice, exactly like conventional crystals we have. And the crystal structure is square lattice if you take nu is equal to 1. But I think later some people checked his calculation, and they found actually if you take nu is equal to 2, you have like a smaller energy. Right? This is also like a famous mistake. He actually got Nobel Prize with this mistake, so it's okay. And if you do nu is equal to 2, you find triangular vortex lattice. And these vortex lattices can be observed in a superconductor. There are like some techniques, and almost all conventional superconductors, like low TC superconductors, they have triangular vortex lattice. But interestingly, if you have a more puzzling unconventional superconductors, some of them have square lattice as well. And there's also the question why they have square lattice. Is it like something to do with Ginzburg-Landau? Should we add some new terms to Ginzburg-Landau? Or is it about the microscopic structure? Maybe the symmetry of order parameter is different. And all of these questions are still a research question today. And if you have appetite, you can spend years to make calculations on that. Good. All right, let's take a break and continue later.